Now I would invite Suhas Dixit to come forward and give us an overview about pyrolysis options, which this great technology might provide for our challenges here, and provide us even first data on a study which he does relying on feedstock material coming from the market. So we are talking about a pilot project, but what we use is on purpose collected empty pesticide containers from the market.
Thank you, Andreas. So out of the total 20 minutes, I'm going to spend 5 minutes explaining what we do as a company, and then rest 15 minutes focus on the pilot that we've done on chemical recycling of plastic waste. So we are APChemi Circular BV, holding company in Netherlands. We operate a lot out of India. Yeah. Okay, thanks. So we are leaders in pyrolysis. We turn non-recyclable plastic, tire and biomass waste into value. We can feed all these materials into the same plant. We have developed 47 pyrolysis plants till date since 2007. We've been only doing pyrolysis since 2007. And we've transformed 179 million kilograms of plastic, tire and biomass, over 1.3 million hours of technology performance into pyrolysis end products. We are supported by Shell Petrochemicals. If you search for APChemi and Shell, it will take you to a couple of websites of Shell. In fact, on 9th, coming Monday, we are given 10 minutes on the main stage of Shell's Premier India event, Change Makers of Tomorrow. We've raised funds in collaboration with Aalborg University, Denmark, to convert plastic and biomass into hydrogen. We are working on up to 240 metric tons per day pyrolysis projects across the world, created 3,000 jobs till date, and we look forward to creating around 10,000 jobs in another decade. We've developed over 7 proof of concepts of chemical recycling, and with the CropLife pilot that we are working with, the number will now become 8. We have 12 patents in pyrolysis and pyrolysis oil purification. So not only convert plastic into oil, but also purify it. So this is the big problem that exists not only for empty pesticide containers, but all the plastic waste that gets generated today. Less than 10% of it is recycled. 90% goes to either landfills or incineration. Around 30 to 40% of plastic waste that is generated today is burned in incineration plants. So from now to 2030, around 3.5 billion tons of CO2 will go to environment because of plastic waste being burned in cement kilns or waste to energy plants. And then huge amount of crude oil and gas is pumped out again to make new plastics. So if you put all the problems together, the challenge is that crude oil is used for producing polymers. These polymers are used by FMCGs and product companies. Then it goes to landfill or it goes for incineration. And even if you convert plastic waste into oil, this oil doesn't have a good quality. That's why it cannot be used back into the production of polymers. So that is the technology gap of chemical recycling. So the way we solve this problem is that we can start with contaminated mixed plastic waste, remove the contaminants and produce purified oil, or even if somebody else produces contaminated oil, we can purify it so that that pure oil can go for production of circular plastics. Now, when it comes to the carbon footprint, of course, mechanical recycling has lesser carbon footprint compared to chemical recycling, and our technology has even lesser carbon footprint. Of course, it is more than mechanical recycling, but compared to conventional way of chemical recycling, we are able to get the job done at around 15 to 20% lesser carbon footprint. So this is the impurity removal efficiency of so removing impurities of pyrolysis oil is the core problem. Converting plastic into oil, this technology is available widely now. Of course, we have an advanced version, but purifying the oil, if you can purify the oil, then oil gets used as a raw material for production of new plastics. And then purification, when we talk about purification, then we are talking about removing around 64 impurities from pyrolysis oil. Anything other than hydrogen and carbon is an impurity. So removal of chlorine, bromine, oxygen, silica, acidic impurities, metal and heavy metal impurities. We have good efficiencies at removing these at lower capex, opex, remove higher impurities at lower carbon footprints. That's the advantage that we work with. So this is the last slide on APChemi as a company. Typical model is convert plastic into pyrolysis. Sorry. Convert plastic into pyrolysis oil, purify that oil so that that oil can be used in circular plastics. So we've received written letters of intent from these global corporates, and from our 3 ISCC plus certified plants already, the purified pyrolysis oil is going to global refinery and polymer producers for production of circular plastics. The main gap that we see in the industry is that there is, of course, mechanical recycling exists and it is doing very good job, but there is either mechanical recycling or there is incineration. In between, chemical recycling solution is not available. So that's where we see an opportunity of reducing the carbon footprint. We've set up our own purification plant to supply this purified pyrolysis oil. Now, coming to the collaborative pilot that we've done with CropLife International, we are extremely grateful to Andrew and Andreas for the kind of extensive involvement that they took during this pilot to guide us and help us understand what are the priorities to make this happen. So we have R&D facility near Mumbai where we have the pilot plant, which reflects our commercial scale technologies at a pilot scale. We customize this pilot plant to process empty pesticide containers with an idea that we don't have to set up separate assets for processing empty pesticide containers. How can we modify the existing pyrolysis plants with less than 10-20% capex so that they start processing empty pesticide containers, and then after that purify the pyrolysis oil so that the oil produced from plastic waste is used for production of circular plastics rather than being used as a fuel. Because if plastic oil or pyrolysis oil is used as fuel, then you're basically burning the plastic waste, then that's incineration. So our objective was always to do chemical or advanced recycling of empty pesticide containers and target that the carbon footprint comes down by around 50 to 70% compared to the incineration. So a member company of CropLife in India gave us two kind of packaging, rigid packaging and flexible packaging. So the pilot was conducted on both. So once we received, we stored it safely, marked it hazardous. So this is how it was stored in our R&D facility. Then this is the entire pilot that we've done. I mean, this is a very simplified process flow chart. The actual flow chart is far more complicated. It is one A1 size big page with more than 30-40 steps. Andrew and Andreas know about it. We discussed the flow chart on how to get the pilot done over the period of 2 months. So this is a very, very simplified version of the flow chart. So what did we do? We took flexible plastic waste and then we shredded it. Then we took flexible plastic waste as it is, pushed it through the pyrolysis and purification technology. And we also washed the flexible plastic waste and used the washed flexible to push it through the pyrolysis technology. Also, we took the rigid plastic waste, then we shredded it. After shredding, it was processed as it is through the advanced pyrolysis technology. And then we also washed it to have the washed rigid plastic waste go through the technology. When we washed, whether flexible or rigid, we had some wastewater coming out. And at the end of the process, we had a bunch of products. So we had pyrolysis oil, we had the pyrolysis gas that was collected separately. Then the carbon black was collected, and also the wastewater, after washing of the empty pesticide container, that also was collected. So during the pyrolysis process, basically the objective was to do chemical recycling of plastics. Objective is to reduce the cost and carbon footprint of managing empty pesticide containers. Cost, as in our projects have very high capital efficiency. We are able to get the capex and opex. Capex around 3 times lesser than a lot of suppliers of these projects. and OPEX around 20 to 30% lesser because of 2 to 3 stage waste heat recovery system, and we are able to purify the oil by ensuring that the use of adsorbents and catalysts is reduced by up to 90-95%. And develop a technology performance statement in terms of safety and efficiency for industry scale facilities that can start processing empty pesticide containers. Of course, objective was also to measure the active ingredients in the raw material as well as end products. So this is the typical yield that we received from rigid plastics. We got around 73 to 78% of oil. Then we got around 2.5% of residue, and rest of around 18 to 25% we got as gas. And from flexible plastics, we got somewhere around 40 to 47% of oil. We got higher amount of residue, 16 to 17%, and then rest was gas. So the difference in the yield between the rigid and flexibles is basically because of presence of polyethylene terephthalate and the aluminum foil that exists more in case of flexible plastics. So all the flexible plastics have aluminum layer inside that comes out with the residue or the carbon black, and the gas increases because of the polyethylene terephthalate that exists in the multi-layer packaging in the empty pesticide containers. So as I said, once we executed the design of experiments, then we tested all the samples in the laboratory. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 samples. Actually, when we did 4 trials, so these multiple samples were sent. Total 30 samples were tested in third-party NABL accredited laboratory for presence of active ingredients, and then we are happy to share some of the results that we got. So as far as the wash water is considered, so let me go a step back. So this particular like flexible and rigid was washed, and then we got wastewater, 2 different samples. So in the wash water, we found that the active ingredients are 5.4 and 8.7 ppm. As per the European legislations, more than 1000 ppm of AI is classifies the material as hazardous. That's what I learned. So the active ingredients in wash water are very low. Of course, this wash water will go through an effluent treatment plant. Now we have an idea of what kind of effluent treatment plant do we need to design when we do washing of this empty pesticide containers at an industrial scale. Then as far as the raw material is considered, in raw material we found rigid unwashed, means without washing, the rigid empty pesticide containers have around 300 ppm of active ingredients. Then after you wash the rigid plastics, there is still 151 ppm left in rigid. That means active ingredients are probably going inside the plastic, which cannot be removed by simple washing. Then in case of flexible plastics, we found that the active ingredients are much lesser even before washing or after washing. So probably this advantage is because of the aluminum foil. Aluminum foil provides a great barrier that doesn't allow the active ingredients to get inside plastic material as such. That's why even before washing, the active ingredients in flexible plastics is lesser, and after washing, I mean, it's very easy to wash aluminum foil inner surface. So the active ingredients are lower, even lower in case of flexible plastics after washing. In case of pyrolysis oil, again we got very less quantity of active ingredients. So in pyrolysis oil, we got 2 ppm, 0.69 ppm, 0.5 ppm, and 0.43 ppm. So these are extremely low quantities of pyrolysis oil active ingredients. We don't see any problem for going this kind of oil to refinery for production of circular plastics. In residue is one of the interesting things that we found, around 0.2, 0.19 or 0.27 ppms of active ingredient in the residue. In case of flexible washed, the active ingredients were below 0 ppm. Now this kind of data is extremely useful when we have to dispose the residue. So we are able to now understand that the residue that will be generated in the process also is not that hazardous as such. We will be able to find utilization for this. In the exhaust gas, so what happened is that we took pyrolysis gas. After we got the pyrolysis gas in the commercial scale plants, we use it as a fuel for heating the reactor. So we burned this pyrolysis gas. After that, we passed it through a scrubbing system, and then we measured the uh, uh, ppm content of active ingredients in the exhaust gas. In exhaust gas, we did not find any active ingredients at all. So this gives us a lot of confidence that we can do chemical recycling in a way that in exhaust gas, there are no active ingredients. In the scrubber water, again, we did not find any active ingredients. We have a scrubber before the exhaust gas. So there also we did not find active ingredients. That's where our confidence increased a little more that we are stopping active ingredients even from going to the scrubber. From pyrolysis gas itself, we are able to remove active ingredient in the modified version of our technology. So to when our objective is to basically reduce the carbon footprint by 50 to 70% compared to incineration. Now, next steps would be to do detailed analysis of this pyrolysis oil and check the impurity profile in terms of, say, halogens, metal or heavy metal, how it is coming into pyrolysis oil, and use our pyrolysis oil purification technology to establish that, okay, this oil matches also the refinery standards. Not only that it doesn't have active ingredients in the end products, but also it matches the refinery standards. We've just got some results and energy balance is positive. So the plant would not require external energy for heating the reactor. We will be able to get the pyrolysis gas as a byproduct for heating the reactor. It will be energy self-sufficient. We will be submitting samples for chemical recycling to global petrochemical companies, and then we will also be submitting a preliminary life cycle analysis of comparing this process with other options that exist in the market. So the conclusion is that our technology works safe for pyrolysis of empty pesticide containers and ensure that the AIs are much lesser than 100 ppm in the end product. As you saw in the oil, it was around less than 3 ppm. We've developed a plug and play technology to process EPCs in the empty pesticide containers in the existing pyrolysis plant with slight modification. And the advantages of such process would be to address all that plastic waste that is not mechanically recyclable, get carbon avoidance credits by preventing incineration, savings by preventing the incineration cost, and upcycling the empty pesticide containers in advanced recycled plastic, which would be food and pharma grade. Thank you.